have to know in the sense of which one is pre-pro, which one is pro, and which one is insulin. And why is it that pre-pro insulin doesn't work and pro-insulin doesn't work, but insulin works. So here's pre-pro insulin. This is just after it's been released from the mRNA, okay? From the ribosome, after the translation of the mRNA with the tRNA bringing the subunits. Okay, so this is pro-insulin. So notice that certain post-translational modifications have been made to the polypeptide sequence, right? So these disulfide bridges have occurred. This links the two subunits that are going to be the final product together. And then this little signal peptide, which is where other things can dock, gets cut off. So here you're going from this is a single chain folded in one direction. You're making disulfide bridges between these two final units, and then you've removed the signal peptide. When you go from pro-insulin to insulin, you've removed this connector because you no longer need it, right? These two subunits are connected by their disulfide bridges, and then this is the active protein. Now we talked before about zymogen precursors, a little tiny bit where insulin is being held in these vesicles ready for release. Does that ring a bell? Okay, so what happens when insulin is held in the vesicles inside the pancreatic beta cells. When it's ready for release, it gets the signal to send it out so that cells can uptake insulin via which GLUT is it? You guys remember? 4, right? So GLUT4 is the only insulin sensitive GLUT. So it can be held like this so that it can be cleaved, and as soon as that last part is cut off, it's ready to be functional. This is one way that we can control how we're using proteins. If we want insulin, like if our body's in a state where it needs insulin, it needs to be ready to go, right? We would like insulin faster than it would take to produce this entire chain. You upregulate the production of the mRNA, then the mRNA comes out and gets the ribosome, then the tRNA runs around and then gets all these little amino acids. Then you put the chain together, and then you have to modify. If you hold it in one of these stations, right, usually in this station, then the final signal cuts this last part and it's ready to go. And we're going to look a little bit more at trypsinogen and trypsin in chapter 9. But does that make sense? All right, so this is an example of post-translational modification. Okay, so how does this work? There are two chains, right? They end up being two chains, but they start out as one chain. All right, and pre-pro insulin. Insulin is the active, so if you go backwards, pro-insulin is the pre-active part, and pre-pro insulin is the pre-active part. Okay. All right, so I just brought up PKU. So PKU is phenylketonuria. Oh, sorry, I got to switch back to my thinking. It's caused by a mutation, one of many mutations, in the phenylalanine hydroxylase enzyme deficiency, so you can't take phenylalanine and convert it to tyrosine. Most are, when I say SNP, single nucleotide polymorphisms. It means there's one base change